So you see this beefy formula here, but if you look closer at it, you can see that it essentially has the same structure as the WHA. I almost said WSA. So we have a constant. Constants can go right in the front. Use a highlighter here. So that's consistent. I have something here that has an H in it, and I have something here that has an H in it. But the difference is I'm looking at a variable H. All right, that height can change. And that should make sense because if you're submerging an object vertically, this part's going to be at a lower height than this part. Every part of the figure is going to have a different height. Right? So I need my height to vary. Right? The length of it, so the length of the figure is going to be the length horizontally, which is weird because notation-wise it seems like you could come up with a better way to represent this, but that's the way they do it. The height is the depth, and the length is the width of the figure. So it's kind of annoying. But I'm looking at something that's rectangular here, so the length is the same throughout. But if I submerge anything else, something triangular or circular, the length of the figure is going to change. So I need to be prepared for that. So I leave my L in terms of some variable quantity. So you say, okay, well, that's length. We haven't really addressed how that becomes area. Well, here's some figure, a trapezoidal. That's going to have some variable length. If I select, I know it's very hard to see, but not as hard as what's on the whiteboard, so I don't feel too bad. I drew a horizontally oriented rectangle, and I labeled it L of Y. All right, that horizontally oriented rectangle is going to have a thickness dy. All right, so what's happening here is the combination of the integral and these two components will give me that area. All right, because what's happening, I have L of y multiplied by dy. That gives me the area of a single rectangle. The integration collects all possible individual rectangles and adds them up, giving us the area of the space. All right, so that's where the formula comes from. It's a pretty nice origin story because it ties together what we're learning about in a science sense, but it also ties that together with bounded areas. All right, so it gives us a little sense of the application of this. All right, so let's tackle a problem or two. Once you get a sense of the technique, they go very quickly, so they're nice problems to have. Find the fluid force on a rectangular metal sheet measuring 5 feet deep by 1 foot wide that is submerged vertically such that the topmost point is 1 foot below the surface of the water. All right, so lots of words. I'll draw the figure, but let me zoom in a little bit. I'll go 200% for those keeping score at home. Double check, make sure I recorded all of that because I felt like it was a pretty solid explanation. Give myself an A-. All right, so I'm going to create an X and Y axis. Where possible, I want to only work with positive numbers. Sometimes I don't have a choice. Let's see if I can get away with it here. We get surface of the water. That's the best I can draw for surface of the water. It's a rectangular metal sheet measuring 5 feet deep by 1 foot wide. Okay, so let me get a rectangle that's 5 feet deep, 1 foot wide. All right, this doesn't look like it. It's not to scale, obviously. But this will be my 5 feet deep, and this will be my 1 foot wide. And it's the topmost point is 1 foot below the surface of the water. So that extra bit of space above the rectangle is that 1 foot. So the boogie board is sent correctly down such that you have a 1 foot of space between the top of the water and the top of the pool. Alright, so what we want to do here is figure out the fluid force acting on this figure. Alright, so arbitrary rectangle. Sorry? You couldn't, because then your arbitrary rectangle would vary in pressure at the different depths. Okay, so we know that if we look at this horizontally oriented rectangle, we have to find a few things. We have to find the height, which is the depth, so the distance from the surface to the water, the length of the rectangle, which fortunately in this case is constant, and then everything else is going to work itself out. All right, so F equals 62.4 for the water. The Y values for which the rectangular metal sheet exists, the Y values go from 0 to 5. Those are the only relevant Y values for any kind of fluid force or pressure. All right, the height of the rectangle, that's the depth below the surface of the water. So that's this guy right here. Well, I know the distance from the x-axis to any point in space is known as y. I know the overall distance is 6, 5 for the rectangle, 1 for the little bit of space above it. So how deep would that arbitrary rectangle be? 6 minus y. All right, so that's my h of y. The length of the rectangle, L of y, that's constantly equal to 1. So I don't need to overthink that part of it. There's so much other stuff I can overthink. And then the dy. Pop that baby in, get some number that'll mean the world to us. Of course not. Oh, why? Why can't I remember? Constants. 0 to 5. Well, 6 minus y times 1 is just 6 minus y. So 6 minus 1 dy. 1092. Shockingly simple. Not the process, but the actual answer. Process takes a little getting used to. 1092 foot-pounds. All right. We know it's foot-pounds because they didn't mess around with the units on us. Everything's in terms of feet. So we're in good shape. The weight densities are in terms of, I already forgot, pounds per square feet. So what that means is that you can rely on the units for your final answer being the foot-pounds. All right? Because I wouldn't mess around with you and like put things in inches and centimeters and stuff like that. I don't think it serves any meaningful purpose. Zoom, page width, bringing it back. A vertical gate in a dam has the shape of an isosceles trapezoid, 8 feet across the top, 6 feet across the bottom, with a height of 5 feet. What is the fluid force on the gate if the top of the gate is 4 feet below the surface of the water? All right, so coordinate axes again. This time I'm gonna, let's not put it there. I'll give it a little bit more space. I'm going to make it symmetric through 2 quadrants, first and the second. All right, so 8 feet across the top, 6 feet across the bottom. So if I'm establishing the origin to be the center of the bottom, I'm going 3 in either direction. Oops. Little taily thingy again. Now, the trapezoid itself has a height of 5. So I'm going to go up 1, 2, 3, 4, 5. I need to go out to 4 for each of these. And this is what my trapezoid is going to look like. And we got the surface of water that's 4 feet above that. Probably made that a little too high based on the scaling. So 5, 4. Just for the heck of it, I'll throw the coordinates in here. It's 3, 4. 3, 5. 4, 5. Got there eventually. The whole counting thing, yeah. This has coordinates of 3, 0. Three units out along the x-axis, then with a height of 5, we had to go out 4. So kind of makes sense. And it also is going to be necessary because this is going to have a variable length. Right? The height is going to be what it was. It's going to be a particular value related to the depth of the object, arbitrary rectangle of the object. But we will have a variable length. So what I'm going to do zoom 300 this time, bringing it in big time, is I'm going to draw an arbitrary rectangle, but only on the right-hand side. Still a dy. All right. So I'm going to double whatever my final answer is. Right? It's going to make our lives a little bit easier. So I have, if I'm just looking at the center of the arbitrary rectangle, the height off of the x-axis, which is y, but I want the other part. I want this guy. We have a total of 9 here, right? If we started at the surface of the water and went all the way down to the lowest part of the trapezoid, it'd be 9 feet. So 9 minus the y that you're coming up to get to the rectangle gives you that piece. But I still need the length of the rectangle. Oh, that's huge. That's perfect. All right, so I need that length. And it's based on whatever this distance is. Distance off the y-axis is known as x. All right, so I just need to find a function x in terms of y. So that's our challenge at this point, because we know everything else. Zoom, page width, bring it back. All right, because we know that it's weight density, 62.4, going from y values of 0 to 5. We know that this is 9 minus y. This is what we need, dy, in order to find our answer. All right, so the minute we come up with that, we have what we need. All right, so let's work off of those coordinates. So we have a linear function, right? A line segment. Let me make a note. Y equals m times x minus x sub 1 plus y sub 1. Point slope form of a linear function. We'll need the slope, change of y over change in x, between these two coordinates. 5 minus 0, 4 minus 3, that's just a 5, right? Choose a convenient coordinate out of what we have available. Well, this is as convenient as it gets. So x minus 3 plus 0. To figure out the slope, we have a coordinate. The coordinate is pretty convenient. Maybe not as convenient as it gets, but pretty convenient. We could solve this. We have really what we have here is a function solved for y in terms of x, but I need it solved for x in terms of y. So first thing I would do, ignoring the zeros, divide out the 5. 5 times x minus, oh, not 5 times x minus 3 anymore. Y over 5 equals x minus 3. And then add the 3. So x would be equal to y over 5 plus 3. So this is my x function that I'm plugging in here, y over 5 plus 3. And that's what goes into the calculator. So it's a little bit of an adjustment, but it's a linear function at least, and we know how to write the equation of a line. It's just in a situation like this, you probably weren't expecting to have to write the equation of a line, so it catches you off guard. But once you realize that that's fair game, and on top of that, not too hard to do if you use the point slope form, it gets a little bit more manageable. Not saying that you're going to like it, but manageable. And so we get nice clean numbers. 13, 9, 36. All right. So I've learned in the past that the first time I explain that, I don't get too many cheers. So it usually requires me to explain it a second time, so I created a second problem related to it. Triangular plate, 5 feet, base, 5 feet, height 6 feet, is submerged in water, vertex down, plane vertical, and 2 feet below the surface. Find total force on that, one face of the plate. Okay, so in each of these cases, it's always one face of the plate. So unless you're told 2 faces, in which case you just double your answer, but I'm not going to, so I wouldn't worry. So the base is 5 feet. So we're talking about a triangle, huh? Put the emphasis on the wrong syllable. I should have just used the triangle tool. The base is 5 feet, the height is 6, submerged in water, and it's 2 feet below the surface of the water. All right, so if the base is 5 feet, then each one of these distances is going to be 2.5, or 5 over 2, or 2.5. It doesn't matter which way you go with it. It's all going in the calculator anyway. All right, so arbitrary rectangle on an interval, a relevant interval. It has a dy. We're going to need 2 of them because I'm doing it the same way. I'm looking at just one side of it. The reason why I don't put the whole thing on the other side, on the side in the first quadrant, is because it would create a gap. If I shifted this whole thing over, I'd have a triangle that went upward. The same orientation. It would have a little gap on the interval in between the y-axis and the function and the bounded region, which would make coming up with your function to represent the length that much more complicated. It ends up not being worth it. Oh, because when I wrote the problem, I intended it to be an isosceles triangle, and you're supposed to read my mind. Typo. Somebody get it. So, 5 feet, 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 5 fe this distance again is y units because this is the distance away from the x-axis. Distance down from the surface of the water would be, we have a total of 8 units, so 8 minus the y that we don't want. So 2 times 62.4 on the interval of 0 to 6, 8 minus y. Now I just need a function to represent this distance x in terms of y. All right, fortunately, this one's a little easier. We have our 2 coordinates, one of which is 0, 0. Now this one, I'll put it in fraction form just to make it a little nicer. So we have 5 over 2, comma, it's 6 units up. All right, so the slope, change in y over change in x, so 6 over 5 halves would be the same as 12 fifths. This one we could just do y equals mx plus b. It's a lot easier. Our function, because we're going through the origin, would be y equals 12 over 5x. But again, I want to solve for x in terms of y. So I'll multiply both sides by 5/12 and get 5 over 12 y. So that's my other part. That represents the length of the arbitrary rectangle. And that's the key to the solution. Because you'll see that there's a lot of consistency with every other aspect of these kind of problems. You're always going to have a 62.4. Your lower and upper bounds of integration are going to be based off of the height of the figure itself. Total distance from the surface of the water to the bottom of the height minus y gives you your h. It's just what you're going to do to come up with the L that's going to make all the difference. So pop it in. I can do a little second interaction here, and then start the slow journey of finding all the edits and probably missing 1 or 2 of them. It's quicker on a handheld. Yeah, almost definitely easier to just retype it. 3744. All right. The numbers, I mean, they're shockingly nice when it comes to these kind of problems because I limit it to linear relationships when you're dealing with the length of the figure. I mean, technically I could say that some object being submerged has a parabolic shape or a sinusoidal shape, but I don't see any purpose in doing that, right? So if you're wondering why the numbers are so nice, it's because we're integrating something that's linear and then multiplying by some really large numbers, so it kind of works out that way. And it's kind of nice. It's nice.